Now, with the chaos of first versus zero order out of the way, I think we can now go to the KE and CL formulas at this point. So this is not going to be like from scratch discussion on mathematics. Okay, so if we are not yet familiar with the conversion of the line equation into something that looks like this, okay, then you may find a better discussion elsewhere. But here, okay, what I'm showing is the formula concentration is equal to the initial concentration times E raised to negative KT, wherein K is the KE and T is the time. And this is something that originates from our pharmacokinetic plot because we should be familiar that the concentration at a certain point, well, the concentration of the drug right now is a function of the time that has already elapsed, right? So like we say that at our number two here, we only have 25% of the drug remaining. And therefore, if you convert this plot into some kind of formula, it would look like this. Now, going further with our fundamentals of mathematics, let's say, what if I'm trying to derive the KE, wherein right now the K is at the exponent? Well, we should remember that to bring this down, we need to multiply both sides by the natural logarithm. So if we do that, that would be distributed. So here, this would be distributed to here. It would become like this. Ln will be distributed to C. So it would be like this. But if Ln is to be multiplied by this, then they would cancel out. And what will happen is this would be brought down. And now we're left with this formula. And so since the constant is already here down, okay, drop down, not anymore an exponent, we could just do simple derivation of the formula to get the KEL. So all I need to do is to like put this at the opposite side, okay, and then put this also at the opposite side. And since this is a negative value, to put the negative sign also at the other side. And so the resulting formula would be the KE is equal to the natural log of C over the natural log of C at time 0 times the negative time. Okay? And so, how do we derive the half-life? Again, let me repeat this from my previous recording. The only time where we have a real half-life is only if we're talking about first-order phenomena. That's why this formula is also under the assumption that we are having first-order kinetics. Otherwise, if it was zero-order, we would use a different formula and not this one. Well, now that we know that, remember that we define half-life is the time that it takes for our initial concentration or C0 to drop down by half, which is, well, if we start with 100, half of that is 50. So just using the same operation we did here, okay, multiply both this and this by ln, and then this drops down. And then if you, this time you want to compute for, if you want to compute for T1 half, then what will happen is that this is the one on the other side. Okay, you have to put this on the other side. And so by doing that, we end up with something like this. Now, since if you divide the ln of something that is half over the ln of the complete thing, it will always become the value 0.693 for, well, I don't know if some of people watching this one are already preparing for board exams or what, but if anyone is watching this for review, that's where we derive our 0.693 from this manipulation right there. And therefore, it's also like saying that the interrelationship of half-life and elimination rate is inverse. The relationship is inverse because it would make sense. Elimination rate basically tells us or suggests how fast something is being eliminated. So if you say fast, how much time would it mean if you are fast? It doesn't require a lot of time, right? You say, I do things very quickly. That means you only need a little time. That's why here, if we have a high elimination rate, you're fast, then that means your half-life, the time you need, is only a little amount. So, if you actually put our, if we follow the logical progression of things, the inverse relationship between the KE and the T1 half wouldn't be really that abstract of a thing. Okay, right. Now, Another thing, aside from KE, that is commonly discussed is clearance. And clearance is the volume of a drug being removed of the body per unit time. And there are really many formulas for clearance, and it might even depend on the scenario which is appropriate. But here, I think my job is not really to go to practical applications or advanced mathematical derivations, but more of showing what is the general formula for clearance. Okay, and here is one wherein we can say clearance is the product of the KE times the VD. Now, with that said, I color coded this time KE in blue and VD in orange because we would remember that KE has its own formula right here. Well, if the half-life is given, and volume of distribution also has its own formula if you know the particulars, which are the AB and CP. Now, if we try to like expand KE, our clearance formula would look like this. You can use this formula if the half-life is given. Now, what if it's not given and you are instead given other values like the AB and the CP? What you can do is to keep KE as it is, but to expand volume of distribution into this. And again, I'm saying that all of this like equal, right? All of these are appropriate. They all say the same thing. You only use which is appropriate depending on what is given. And even going further with these formula manipulations, if I can play around with the formula of clearance, then doesn't that also mean we could play around the formulas of KE and VD? So for example, I can also say that KE can be computed as the CL over VD if we use this formula, right? Um, um, put this on the other side. So KE is equal to CL divided by VD. Or if you expand this, the VD is AB over CP, right? But it's at the denominator, so it's inverted, CP over AB. So KE can be equal to clearance times the plasma concentration over the drug dose. So it really depends on what you need at the moment if you're being asked a certain computation question. As long as you know how to play around with these variables or these parameters, then you can hopefully use what is necessary. And one more thing before I end is that in real life, the clearance is very important because it tells us how efficient a person is in getting rid of substances from his or her body. Of course, by substance, I'm referring to drugs in the context of pharmacy or in the context of pharmacotherapeutics. Sometimes, if the clearance of a certain drug is really large, it means it gets eliminated quickly. That's a consideration you have to do. So, do I increase my dose because the clearance is high? Of course, I should, because if the clearance is very high, the drug is gonna be eliminated very quickly. So I should add more drug for it to have some kind of effect. Or if the clearance is very low, the patient has some kind of disease and the clearance goes down. Maybe I need to reduce my drug administered because the patient's not good at getting rid of it. So I should also reduce the amount I'm giving because it will accumulate if I don't. So those are practical implications in advanced discussions that will be important as with regards to the significance of clearance.